All right, so we're going to be working on 10.2 today. So let's do that. Let me get this shared screen here. I'm going to share my big screen right here. Okay, so we're working on 10.2. And we know that 10.2 is comparing two means. And what I'm going to work with a little bit more specifically is I'm going to talk to you a little bit about 10.2, and then I'm going to look with the cholesterol problem. So I've kind of shaved down our 10.2 PowerPoint here. Some things we want to talk about when you're using the two sample T procedures wisely. Don't use pooled data. Okay, that's only for two samples Z test for proportions. So that's when we have the null hypothesis that the proportions, when we subtract them between each other, there's no difference. Or essentially they equal each other. So when they equal each other and make that assumption, then we can pool that data. But that only works with proportions. So don't try to do that here. We're not going to pool. And in fact, we'll see that our default is set to no to pool because it's very rare that we would do that. So we wouldn't see that here in AP stats. We know that it is, we're safe using two sample T procedures for comparing two means in a randomized experiment. We don't need to check the 10% condition in an experiment because we aren't sampling. We do not use two sample T procedures on paired data. So I think we'll see this in the note packet 10.2 number 7. When do we use it, or is it safe to use on paired data? Remember that paired data was back in chapter 9. And in chapter 9, we didn't really look at two sets of data. We took two pieces of data, we found their difference, and then we did a trial on the mean difference, treating that difference basically as one set of data. Here we have two sets of data, and those data aren't necessarily going to be something that we can pair. Because so the nature of it, if we could pair the data like before and after with the heartbeats, when we compare a person to a person receiving two different random treatments, we can do that. But we don't see that here in our two sample T procedures. So we wouldn't use paired data here. Another thing we have to make sure that we really have to make sure that we're randomizing. We have to make sure that we have a random sample. Otherwise, we won't be able to make generalizations out of that. Let's say that we have 50 people that volunteer for an experiment. We have to be careful because the results that we get from that may be hard to take outside of those people unless we can feel that those people are well representative of the population. So we just have to be careful. We always need randomizations to help us get rid of some bias there. So let's move on to the cholesterol check. So we can see here in the cholesterol check, usually in class I already read this to you, but if you need to read it, you can pause it and take a look and then start the video again. So we're taking a look at this here, and it looks like we have the cholesterol level for different humans. We want to look at 100 people. We took them, they had a cholesterol level between 250 and 300, and then we put them into two treatment groups. One of them is going to get a standard medicine, and one of them is going to get a new drug. Notice down here too that this is an old AP exam problem. It's from 2007B AP Stats exam number 5. And towards the end of this, I'm going to remind you how to go and check those answers online when you know what problem it was from the past. So the first thing it says, why is this experiment rather than an observational study? Okay. You can, if you don't want the answer right away, I'll give you a second to pause it before I'll tell you. But this is definitely something that you want to try to think about yourself for a second. Why is this experiment rather than an observational study? Well, right here, we see that it said two treatment groups. Because this was, because the people were given a treatment, that's why it's an experimental study. We would say that this is an experimental study because we are assigning treatments. So let's start over here. Let's start writing up that problem a little bit on the cholesterol check. So we would have number 1. This is an experiment. Because we are assigning treatments. So that's really important. All right. That is an important part of this problem. And we can see this is a great nature of a free response question when they're starting to combine different things that we have. What we're currently doing now is combining with the ideas that we did back in chapter 4, which is very common in free responses. They don't have a lot of free responses that they can ask you. So they try to combine different ideas and see how they intermix there. And that's a good thing to practice. Number 2, diagram this experiment. So now we're still looking back and to do our work back in chapter 4 to diagram this experiment before we do some of our new stuff. So let's pop over and let's work on that. So remember that we have experimental units, or if we were using humans, we would call them subjects, right? So we're going to take a look at our experimental units here. And so we have about 100 people, and those 100 people had something that was very special about them. They had that cholesterol range. So I'm going to say 100 people with cholesterol levels between 250 and 300 milligrams. Okay, and those are going to be my experimental units there. And so what did we do? Well, they went to different treatments, right? We had a treatment 1 and we had treatment 2. So we're going to send 50 of them. 50 of these subjects, treatment 1, standard medicine. And treatment number 2, we had 50 subjects that got the new medicine. Now, we know that's important. We can lose some points on here if we don't tell them how we were deciding what trend we went to. We assign them, they were random. So we want to make sure that they randomly went there, okay? And then what we did is we brought them both back together. And what we're going to do is we're going to compare those results. So we know that we're going to compare the results, and what we want to do is we want to make sure that we compare the results. We want to put that in context. So actually what we're going to do is we're going to be comparing the mean decrease in their cholesterol level. And we didn't talk about it before, but we know that we would do that. We would do that with a confidence interval or significance test. All right. So that's the diagram. Remember that we need to start with our subjects, our experimental units, talk about how they were put into our different treatments. It's important that we said 50 and 50. They don't have to be equal, but we want to know where all those 100 people showed up and where they went. And we want to come back and compare the results. So that's what we're looking at now. So that's the first 2 parts of our question. So let's see what they had for us next. So we took those 100 people. It looks like after the 3 weeks, we had the 50 subjects and the 50 subjects get a new drug with a standard, got some means and standard deviations there. And then they want us to say, does the new drug appear to be more effective than the standard treatment than lowering it? Give appropriate statistical evidence to support your conclusion. Okay, so basically what they're doing here is they're opening it up for us to make a call. What are we going to do? Are we going to do a significance test, or are we going to do a significance interval? And I think what I'm going to do is I'm going to run the test first, and then maybe if we have time, before the bell rings, maybe we'll talk about the interval as well. Okay, so let's see here. So I'm going to run a significance test. That means I'm going to go full phantoms. All right, here we go. So I'm going to do as much as I can on this page, and then I'll just keep going as it goes. You can always pause and go back and forward as you need to. All right, so first thing about phantoms is P, and I'm going to identify my parameter of interest. I'm going to use mu sub S, and that's going to be for the standard drug. And I'm going to use the mu sub N, and that's going to be for the new drug. So those are the two that I'm going to use here. So the mu sub S is going to be my mean decrease. In cholesterol levels for the standard drug. And my mu sub N is going to be the mean decrease in cholesterol levels for the new drug. All right, so that's my P. I'm going to go with my H. I want my hypotheses. I always have H of O and H of A. So H of O, I think what I'm going to do is I'm going to, I think the key that we have online, we do it this way. We say mu sub N minus mu sub S, and we're going to do the null is dull. There's going to be no difference, right? And then mu sub N minus mu sub S, and then we know that that's going to be 0. It's always going to be the same here and here, but we have to think about what are we looking for, okay? What are they asking us to find? So let's pop back over real quick and let's see. Does the new drug appear to be more effective? So we would want the mean decrease in the new drug to be higher, okay? So if we pop over here and we look at mu sub N minus mu sub S, if we want N to be higher, so that's going to be a higher number, that's going to be a lower number, then when we take a look at these, we want this to be a greater than. Now, for some people, that can be tough to think about. And that's why a lot of times in notation, what we see is we see this written a little bit different. Sometimes they'll actually solve and put these on the other side. So I'll put these in parentheses here. But mu sub N, if I put mu sub S the other side, this would be mu sub N is equal to mu sub S, right? And then over here, this would be the mu sub N is greater than mu sub S. So you can see that when you solve it like that way, then it's a little bit easier to see. For me, oh, I want the mean decrease of N to be bigger. So sometimes we'll see the hypotheses written that way when we're trying to figure out which one we want to do. Okay. Let's go to phantoms P8, HA. So A is our assumptions. So we have to take a look at random. And the randomness here is not that the fact that we had random subjects, because remember, we can't randomly pick people and get them to be in that cholesterol range, but we still need randomness to take care of it. So what we did with randomness here is we took care of the randomness by randomly assigning them to treatments. Okay? That's really what we're looking for here. So subjects were randomly assigned to treatments. That's important. We need that randomization. But it's different than what we're used to checking for random. Right? And then we want the 10%. Remember, we talked about that 10% aren't needed when we are, because we're not randomly selecting the sample, we're doing an experiment. Okay, it is an experiment. And then the last one we have is large counts. In large counts, we have to make sure that we're doing it. And so how can we do large counts? We would either have to know that the populations in themselves, they were they were normal. We don't know that. And we don't have access to the grid, to the graph here, but we do have something special that we can check, and that we know that both of the sample sizes, both of the treatment sizes end up being greater than 30, right? So we can look at it, we can say n of n was equal to 50, and 50 is greater than or equal to 30, and n of s was equal to 50, and 50 is greater than or equal to 30, right? So this is okay to use the t distribution. So all conditions are met. So we're going to go forward here. We're going to talk about that. And I'm going to try and switch n. I'm going to try and get n on the bottom here. So all conditions are met. We can do a 2-sample t-test for the difference of the means here. And that's usually what we're looking for. We're usually looking for the means. So it's a 2-sample t-test for means. So I'm going to switch pages here. And remember, it's always important to save your work in case you need to go back and talk to people about that. So you can definitely do that here. All right, so we left off on n, so I'm going to get to t. T is what next? Okay. All right. So we're going to work on t. We're going to work on a sampling distribution. And this is going to be the difference of means. Notice that we've switched to x bar because our sampling distribution is about our sample, not our population. So the hypotheses are going to have the population parameters, mu. This is the sample, so this is going to see our x bar and our x bar. Notice also from our sample info that we had, they told us that x of n, that was equal to 18. And we had that our standard deviation of n was 12. And we had our sample mean of s was 10. And we had our sample standard deviation of s was 8. A whole bunch of symbols to keep going around there, okay? And again, going back to our PowerPoint slide, we just saw that right here, okay? So we have our 18 and our 12 for our new drug 18, 12, and then we had our 50 subjects, and we had the standard drug, which was 10 and 8. Okay, so that's going to be some good stuff to work with here. We're going to need those numbers for ourselves. So we know that this is always going to be centered. It's going to be centered on our claim, which is 0. Okay. And then we have to figure out, this is a t distribution. So we got to figure out some certain things. I've got to figure out what's the degrees of freedom, what's our standard error going to be. So let's do the standard error first. Okay. So what I'm going to do is I'm going to take s of n, and I'm going to take that squared, and I'm going to take it over n of n, and I'm going to take the s of s, a lot of fun things here, and I'm going to put that over n of s. All right, a lot of fun symbols there. So I know that this is going to be 12 squared, and that's going to be over 50. And this is 8 squared, and that's going to be over 50. Remember that this is the same thing that we saw before. It's just that the variances always add. So we, instead of taking just the square root of the standard deviations, adding the standard deviations, we have to add the sum of the error together. We have to add the variances because the variances always add always, and then go from there. So this is going to be about 2.040, right? And also remember that we're not alone on ourselves there. We have our, here it is, our student resource packet. And we can see that here are our standard deviations right here. This is a 2 population, right? Sample deviations from means. And right here, we can see that equation for us. So we're not by ourselves ever. Up here in the 2 populations, adding the variances here, down here in the means, adding the variances. So we have help there. We don't have to worry about remembering that all by ourselves. So we have this distribution. It's centered at 0. Okay. And it has 2.040 for the standard deviation. Now, that's a little incomplete with that notation. Notice that I have t, and I have 0, and I have 2.40. But the problem is that we don't have, right here, we haven't talked about what the degrees of freedom are. And that's important. Remember that degrees of freedom are really tough to find with, it's a really huge equation, and we know back from the PowerPoint. So we kind of released you from some of that, and we're going to show you how to do it on the calculator. And what's nice is it's kind of the same moves that we're going to do to check our test later, and we can check to see what we have. So I'm going to show you that, and we'll reference it a couple times here. So I'm going to bring my calculator over, and I'm going to go to Stat, Tests, and I'm going to go to a 2-sample t-test because that's what we're working on here. Okay. Notice that when we have data, we can plug that right back in and say we have list 1 and list 2, but we don't have data here. We have statistics. So that's what I'm going to do. I'm going to put the statistics in that's been given to me from the problem. So my x1, I called it, that's going to be 10, and this is going to be 8, and there's 50 of them. And my x of 2, I'm going to make that my, excuse me, I make that my second set. So that's going to be my 18 and 12, and that is going to be 50 as well, okay? Well, now we have to try and figure out, well, which calculator move are we doing this here? Which one are we trying to set up? And so this is a little bit different from what I have, but remember that I want x1, which is my standard. You see I put the 10 and the 8, so that goes with the standard. I need that to be smaller than my, my new one, so it's going to be right here. It's showing us that x2 is going to be bigger, right? So we're looking for mu2 to be bigger there. So I'm going to go down and I'm going to calculate it, and that's going to help me get my degrees of freedom. We can see that the degrees of freedom here are pretty high, 85.37. So if I was going over here and I want to make this more precise, I would say this is 85.37. So that's the T that I have there with that many degrees of freedom. So what I'm going to do is I'm going to show you this, a little of it worked out, but we're going to let your calculator do the work for you here. Okay. So the calculator, you don't have to, I want to show you the math because that's what I do, but the calculator is going to help us out once we get there. So again, I'm going to go over to T, and here's the big equation for T. We're looking for x of 1 minus x of 2. And that's going to, we're going to subtract the claim from that. And I have a really crazy standard deviation here. Okay. Well, I know this is 10 minus 18, and that's minus the claim of 0. And we can see from up here that we have this is going to be about 2.040, right? So we have the claims, we have 0.240, so we get that t is equal to about 3.9. Excuse me, so it's 3.922, okay? And where did we see that before? Well, we see that in our calculator here. Okay? Now, if you take a look at it and you do the 10.98 and the 0, you're like, oh, that's interesting. When the 10 minus 18 divided by 2.040, that gives me a negative. Well, I got to divide it. I can't just type it in. Hold on. 2.40. That gives me a negative, right? So basically, if you're doing it this way, we have the negative 3.94. So why do I see a difference between the negative 3.94 and when I go out to the test, right? When I go out to the test, we had a 3.92 positive. And that's basically along the way is I switched my U1 and my U2, okay? So I think I need to go back because when I'm putting that 10 first, that's my standard, right? So I'm putting my 10 first here, 10 minus 18, then that's going to be 2.04. If I'm going to do my new first, then what I need to do is I need to take that and say, okay, this is really the 18 minus 10. So if I do the 18 minus 10, and then divide that by 2.04, what are we going to get? Positive 3.90. So I had some people ask me, what happens if I mix those up? But remember, this is symmetric. So the tail end, the 3.92, whether that's greater than or less than, it's going to give you the same p-value if we're looking off in that direction. So if you mix those up, that's okay. You probably just ordered it up. You probably just did the order of it. You have to be careful and say, with your notation, what's first, what's second, how are those going to line up, okay? Just a simple switch on the calculator. Don't worry, it's okay. All right, so we're going to go to the O now. Obtain the p-value. So I'm going to use TCDF. And with a positive 3.922 to something really, really big. And my degrees of freedom were 85.37. Okay. So remember that what we have here, this is lower, this is upper, and this is degrees of freedom. Okay. So I'm going to go to my 3.922. Let's get back in this stat. And second distribution. This is a TCDF. 3.922. Something big. I'm kind of really overkilling it on the big there. But, it won't hurt. I get a p-value that's really small. Wait, what is that? How can a p-value be 8? P-values are supposed to be between 0 and 1. Well, we got to look at this little -5 right here. This is scientific notation, 0.000888457, right? So that's in scientific notation. Remember, p-value would never be higher than 1 or less than 0. So if you see something there, there's something in notation. So that means that my p-value, we can kind of virtually say that it's 0. It's practically 0. But we have 0.123488457. Okay. Really, really small. So what do? Well, it's time for us to make our decision. And when we make our decision should always be about H of A, right? I'm sorry, always about H of O. And then when we make our statement, it should always be about H of A. So our first thing is about H of O. I'm going to reject H of O. Remember that most modern rubrics need to see a comparison between your significance level and your p-value to help support that decision. So I'm going to say I did that because my p-value of 0.00008845 is less than my significance level, alpha level of 0.05. Okay, really small. Okay, so that's about H of O. I reject HO. What does that tell me about H of A? I'm going to talk about H of A, and I need to put it in context. So I'm going to say the evidence suggests, or we have significant evidence to conclude, that, and we got to go back and see what we wrote for it. Let's see here. So for H of A, we said that the difference between the mean of N and the mean of S is going to be greater than 0, or we basically said that the new treatment, the difference in the decrease, the mean decrease in the new drug is going to be greater than the mean decrease in the old drug. So we can kind of write it in either one of these contexts if we want. So I'm going to say the evidence suggests that the new medicine has a greater mean difference let's say mean decrease in cholesterol level. Than the standard medicine. And I might even go as far to talk about that it wasn't these unique in this group of people, the people who initially were between 250 and 300. Okay. So let's take a look at some of the things that we did here. Let's go back to stat tests and go to the 2-sample t-test. Go back down here. We don't need to pool. The pool is when we know what the population standard deviation is, and we don't. That's impractical. We won't know that. So look at some of the things that we got. Right, we have the p-value of negative or positive 3.92, depending on how we set it up. We're gonna get that right here. Depending on how we set it up, and we're gonna get our p-value that's really small. And we also got some help getting our degrees of freedom. And in fact, if you're just trying to find the degrees of freedom and you have the summary statistics, just run the test with the significance test to help you get that. So we can see that we got the significance, right? There's the degrees of freedom right there, and we got that from the line DF. Okay. So kind of a bonus here, what would we expect to see? And the problem's done. So you can hit stop, rewind, pause, whatever you want. Let's talk a little bit more about it here. But what would we expect to see if we're doing a significance, we did a significance test, we did a confidence interval instead. So I'm going to go over to tests, and I'm going to go to 2-sample t interval. And what's nice is the data is still in there. So when I ran a test here, I ran that test and I said, okay, I'm good to go. I just have to make sure I change the confidence level to what I want it to be. We can see that we go to calculate, and we can see in the direction that we did, because remember mine was negative, that there was a greater increase from 12 to 3.9. So that means I put the standard in first. So putting the standard in first, the standard, and when we look at the new, it shows that the standard had a lower decrease. The standard was a lower decrease of negative 12, almost to -4, or I'm sorry, a little past -4. So a big thing is that we don't see there is we don't see the 0. If we had a 0 in there, that would be that there is a plausible value is 0 and that there really is no difference between the two. Would be a plausible value. So this is great. We see that with the negative, the entire standard is below. If we were to go up and to switch, so we can go to our 2 sample T interval, and maybe instead of doing the old drug first, we'll do the new drug first. So that would be my 18 and my 12. And that had 50. And then when we were looking at our standard drug of 10 and 8, right? So now what we're doing is we're comparing and seeing the new drug minus the standard, and we calculate it. Then we see the opposite. We see, well, when we take the new drug minus the standard, I'm 95% confident that it's anywhere from 4, a decrease of 4 to 12 more, higher. So I think, again, I think that's a good thing to go. So we're looking here, and that's pretty good. So what are some other things that you can do here? Well, if we go back to our cholesterol check, we can see this is the 7000B AP stats exam pre-response number 5. So we can go out and try and find that. It's not too hard. So we have the AP stats. Well, I already looked it up from before, so it's up there. And we can go in, and you want to go past kind of where it says secure media, because you can't necessarily get in there as a student. But here it is here. And I'm going to go down to question number 5. And this is really neat. This is back in 2007. So the language that we talk about may be a little bit, not antiquated, but a little bit different from what we have. So they have the intent of the question. It's experiment because they impose treatments. Here is part B. So basically they're taking a look at and kind of chopping it up. And we kind of broke this up a little bit differently, ask you a little bit different questions. On it, we told you to diagram the experiment so you get a chance to practice. They wanted you to set up a hypothesis, check the conditions, and then run the test. So you can kind of see how they had it from general there. This is what's really, I think this is interesting to me to see what kind of points they would assign to it. So in part A, was essentially correct if it says experiment because of treatments. Wow, you have that down, you have 1 out of 4 points, boom, already nailed. And this year, part B was identifying 2 populations with a correct hypothesis. So just another part for hypotheses there. They were talking about both conditions are checked, and then essentially correct if the p-value and the correctly interpretation was there. So really that wasn't too much. We added a little bit more to this for practice, but we can go back and see that too. And again, you have the whole year of tests here, so you can see what they wanted to look at, what the test was that year. So I think that's pretty neat. So that kind of wraps up 10.2 for us. Remember, we described the center shape and spread of the sampling distributions for the difference of 2 sample means. Not that much different from 1 mean or from 2 proportions, just kind of melding those ideas together. Tell where the conditions are met for doing an inference. We kind of see that in our problem. Same thing as before. Random, 10% if it's needed, large counts. Construct and interpret a confidence interval. Construct perform a significance test. And then when it's appropriate to use 2 sample T procedures versus paired procedures. That kind of wraps it up for us here. And what we have, please continue if you have questions to let us know, and we'll do our best to answer those. That's about it for now. Again, let us know how we can help. Thank you.